In this example, we look at another method of solving a non-homogeneous linear differential equation. And we'll use a method that's similar to what we've looked at before. First, we'll solve the differential equation pretending that it's homogeneous and come up with a solution yc, the complementary solution. And then we'll go back and find a solution that takes the secant into account, and that's the particular solution, and add those two together to get the general solution. Well, first let's solve the homogeneous equation that's derived from this equation. So we'll write down the auxiliary equation, m squared plus 1 is equal to 0. Solve that for m, so m is equal to plus or minus the imaginary unit I. And then we can use that to generate the complementary solution, yc. So that's c1 cosine of x plus c2 times sine of x. So usually it's very quick finding the complementary solution, and all the work that needs to be done, it usually comes from the particular solution. Now the approach that we're looking at today in this video will generate our particular solution by patterning that after the complementary solution. So the complementary solution is c1 cosine x plus c2 sine x. For the particular solution, we'll use something similar, u1 cosine x plus u2 sine x. And there is a difference between the two. In the complementary solution, we're assuming that c1 and c2 are constants. But in the particular solution, we're allowing those to be functions. In other words, we're allowing those to vary. And that's where this method gets its name, variation of parameters. Now the method for solving for the two functions u1 and u2 just applies a formula. So if you're interested in where the formula comes from, there's an explanation in the book. Right now, though, we're just demonstrating how to apply that formula in this particular case. So the first thing we do is we go back to our complementary solution, and we notice that it's a combination of two different functions. It's a combination of the cosine of x with the sine of x. And then we form the Wronskian of those two functions. So that's w is the determinant, cosine of x, sine of x is our two functions, and then the second row on the Wronskian is just the derivative of the first row. So we differentiate and get negative sine of x and cosine of x. So to compute this determinant, we have to multiply across in both directions. So first we have cosine times cosine is cosine squared of x, and then we subtract and multiply across this way, so we have sine of x times negative sine of x, so that becomes plus sine squared of x, and cosine squared plus sine squared is equal to 1. So we have our Wronskian is equal to 1. Now there are two other determinants that we need to compute. There's the determinant we'll call w1. We get w1 from the Wronskian determinant by replacing one of the columns. We'll replace the first column in the Wronskian by a 0, and the next entry will go up to our differential equation and get this function right here, secant of x. But then the second column just comes directly from the Wronskian. So sine of x and cosine of x. Let's compute that determinant. So we multiply across this way and get 0. Multiply across this way, we get sine of x times secant of x. And just simplify that. So sine of x times secant of x is equal to tangent of x. So we have negative tangent of x for w1. Now there's another determinant called w2. And we go back up to the Wronskian determinant, this time replace the second column. So the first column we keep, so cosine of x, negative sine of x. The second column is replaced with the 0 and the secant of x. And we compute that determinant by multiplying across both directions. So we have cosine times secant. And then minus 0 times negative sine of x. Cosine times secant is equal to 1, so we come up with W2 is equal to 1. Well, next we have to use these three determinants to solve for U1 and U2. The method that we're using is known as Cramer's rule. And again, we're not going into the details of that. There'll be other textbooks that describe what's going on with Cramer's rule, but we'll just show how to apply the method for this example. So first we'll start with U1, and we don't actually get U1 directly, instead we get the derivative of U1, and that U1 prime is equal to W1 divided by W. And so our W1 is equal to negative tangent of x, and W is equal to 1, and we end up with just negative tangent of x. So to get U1, we have to integrate. So we'll have the integral of negative tangent of x, and that's equal to negative logarithm of the absolute value of secant of x. Now there are actually different forms for writing this integral. So the integral of tangent can appear different ways, and another way of writing this would be the logarithm of the absolute value of cosine of x. So that takes care of U1. Let's go on to U2. And U2 prime is equal to W2 divided by W. So W2 is 1, and W is also 1, so we get 1 there. To solve for U2, we have to integrate the 1, and so that integrates to x. And so now we've solved for the two coefficient functions, the U1 and the U2. So we have U1 up here and U2 right here. And we'll just put those in here to solve for YP. So we write down YP. The first thing we go to is the U1, which is the logarithm of the absolute value of cosine of x. And then that's being multiplied by cosine of x. And then we have U2, which is equal to x. And that gets multiplied by the sine of x. And so that gives us our particular solution. So we have both parts. We have the complementary solution back here, and now we have the particular solution. And so if we add these two solutions together, we'll have the general solution for the differential equation up here. So let's write that down here at the bottom. So y is the general solution, and it's equal to yc plus yp. And so our yc is up here, c1 cosine of x plus c2 sine of x, and our yp over here. So we have the logarithm of the absolute value of cosine of x multiplied by cosine of x plus x times the sine of x. And so now we have the yc combined together with the yp, and this is the general solution for the original differential equation up here, which is a non-homogeneous linear differential equation.